Okay, I'll just start recording.
Okay, so should I start? Yeah.
Yes, yeah, you can start sharing your slides. I will just give a brief introduction. So, and maybe I'll also send one more reminder, the last reminder that we are starting. And okay, Rafał is joining, the next person. Okay, good. Hello everyone, welcome. Thanks for joining our talk. So, one of our jury members, Dr. Shaeema Zaman Ahmed from Aarhus, from Denmark, will give a talk about quantum game development. So I hope you will enjoy it. This talk is recorded, so later we'll publish the video on our Discord. And Shaeema, the Zoom is yours, so you can start.
Okay. Hello, everyone. Really nice to be here at this talk, and I wish you good luck for the hackathon coming ahead. So today I wanted to share a little bit of my own experience of making a game during my PhD. So this next half an hour is going to be about the game and sharing my experience. And then just a little bit about me. I am originally from India. I did my master's in physics from University of Delhi. Then I worked as a science communicator and educator. That's where I sort of started experimenting with using games, doing citizen science games, doing workshops and to work with schools. This was mostly on astrophysics, but then I was sort of also broadly space based, doing other things in quantum physics as well. Then I came to Denmark. I found this really nice position, PhD position on quantum games. And I think that was something that it was on quantum physics and games. So it sort of brought everything together, which is like research, education, and outreach. And I thought, okay, this is something that I would really like to do because I wanted to look at this sort of one position where I could do education and outreach as well. So after my PhD, which was I finished last year, and it was on quantum games. So one of the main things was to design a game and do research on that game, and which is what I'm going to present today. And after my PhD, I started my own company. I was wondering, what should I do? Should I continue with academia, do a postdoc? But I had some ideas in my mind about how to make sort of quantum physics learning fun and innovative. So I decided to open my own company. This is about me, and this is the outline of today. Like I mentioned, I'll give an introduction to the game. The game is called Quantum Moves 2. Don't know if some of you have heard about it or not, but don't worry, I'm going to give like a introduction from scratch. So yeah, and then I'm going to share my own game development experience. This game took 2 years to make, and it was interdisciplinary team with me and game designers. So I'm going to share that experience of who were involved and how did we divide the work and what were the challenges, what were the fun things, and so on. Great. So Quantum Moves 2, it is a citizen science game in quantum control. So citizen science game is a game where anyone can play the game without having any knowledge about quantum physics. And from the name, it's Quantum Moves 2. The game is a simulation of problems in quantum control. Okay, and then I'll just give maybe a brief, maybe some of you know already what is quantum control. Quantum control is the fundamental requirement today when we talk about quantum technology. We need to be able to control atoms in a particular desired way so that we can achieve certain entangled states or certain superposition states. So it's really the fundamental level of being able to control atoms. And that in itself is a really hard problem because you have effects like decoherence. You have to be really fast in doing these control experiments. So it is a complex problem in quantum physics research. So we decided to take this problem and say, okay, how can we gamify this and create a platform where players can experiment with some quantum control problems. So to design the game, we first had to work out what is the mathematical framework that we want to simulate in the game. So here is a little bit of like Okay, maybe I'll just take a laser pointer. It's easier. Yes. So we started out with, you have a quantum system. This is just on a theoretical level. You have a quantum system. You can do something with the system, and you need a function, which is u, which is a function of time. So this function changes with time. So, and this function then affects your Hamiltonian. So, and by using this function, changing the Hamiltonian, you can control the atom. You can change some properties in the atom. Okay. We particularly looked at a problem called a state transfer problem, which is just, you have an initial wave function, and then you move it over time t, and then you reach a final wave function, and then you try to see how similar is this final wave function with a target wave function. So we move from some initial state to a final state, and that final state is some desired state that you want, and then you see what is the overlap. So mathematically, this is calculated by this overlap, which we call fidelity. So this is sort of the basic theory behind what we simulated. So we had to first work out all this math and say, okay, what kind of problems we want to look at, what kind of function ut would be, u as a function of t, and so on. So, and then what happens is, this is also when we want to solve a quantum control problem, let's say without a game, then we use a lot of computer algorithms to find some initial control functions, which we call u not t, which is like what we call a seed. A seed is something, if you think about how you have a plant, you take a seed and something grows from that seed. Similarly, also for a quantum control problem, we consider a seed, which we keep on iterating over and finding something better. So if you start from u0 to u1, u2, and so on. And at every point, you calculate the fidelity. And this fidelity is calculated by this relationship here. So there's all of this that needs to be worked out. And then currently we use algorithms to figure all this out for us. And then finally, when we find something that this fidelity is very close to 1, then this particular control becomes something what we want, which is called an optimal control that we want for that problem. Okay. Now this is all mathematical and theoretical, but how do you show this in a game, right? And how do you sort of get a feel of what are we doing? So I like to describe it by this little story that I have here. So imagine you're a pirate and you have a target ship and you want to shoot this target ship. So then you think about, okay, how far is the target? What's the wind? So you sort of make an estimate of what angle your cannonball, it should be aimed at, so that you have the cannonball that can hit the target. So you first make an estimate and then you guess, okay, and this guess is based on what are the constraints you have. Okay, there's wind. So you have to think about how far it is, because depending on the distance, this angle will matter, because you want a kind of parabolic thing that will hit the target, right? So anyway, you experiment and then you actually try it out. You said, okay, let's try it out. And then you see, it actually didn't quite hit the target ship, but it reached before, like a little before that. But it's still not that bad. So what you do, you again iterate over this, and then you find a better estimate. And this is exactly also what we do in quantum control. We have a problem and we want to say, how do we best solve this? Okay, let's try out with this guess solution, because we think this should work based on the problem. You know some properties of the problem. You know how atoms will react in a certain way, or what energy levels the atoms are, and then you do estimate. And then you just keep on finding better and better solutions by doing iterations. So it's like saying you're going for a hike and you find, but sometimes it's really hard because you keep on finding these solutions and you keep on finding better and better solutions. So where do you stop? So there's a lot of algorithmic computational power that you need to find the best solutions. And for example, you're going on a trek and you're blindfolded, and then you keep on walking and walking, and then you find a peak and you think, okay, this is the top of the mountain range. But actually, it turns out that if you walk further, there's going to be a higher solution, a higher mountain peak. And this is why the whole problem of quantum control becomes very, you need to find many, many, many solutions before you're sure you have found the best solution. So it's like a game to us as researchers, as scientists. So we thought, why not actually make a game out of it, where we sort of, what we call is exploring this landscape, exploring how many solutions could be there, exploring what are the different ways to get the solution. Currently, it's been done by purely computational approach. You have some set of instructions that you put into a problem, and then these algorithms are called grape, stochastic ascent, like many, and they're all inspired mostly from computer science. With these computer science algorithms have been taken and sort of given a twist to be applied to quantum physics problems. The other method that we thought, okay, it could be interesting to find out what if we made a gamified version of this problem and let people play it without having any knowledge of the problem. Let's see if they find something interesting. So we designed the game, and we said we mostly went to high schools. We also taught them a little bit of basics of quantum physics, and then they played the game. And we collected all that data. And when we wanted to find out if the citizen science approach is comparable with a computational approach, and what also happens if we combine a little bit of both, a little bit of computation and a little bit of citizen science. So human solutions given by the players and a computer generating solutions. And if we combine them, if that's also a good way of finding the solution. So that's what 2 years of my PhD was, where I had to design the game, find out, analyze the solutions and see, okay, how did players provide these solutions and if these solutions are good. Yes, and right. Okay, here maybe I just want to say, if there are any questions, feel free to interrupt me, okay? Because sometimes it's just easier. I see something is in the chat.
No,
okay.
but yes.
Yeah,
It was not a question.
But yeah, good day also. Yeah. So yeah, because
maybe yes, maybe you can just make a quick pause and ask people if they have some questions now.
Yes.
All right. Any questions? I can see that we have already 10 people, so maybe there are some questions now. I don't see any questions. Also, if there are any questions, feel free to post your questions on the chat, or you can unmute yourself and interrupt, I believe, right? So it will be more interactive, but anyway, as for now, I believe we can continue.
Okay, fine. So, all right. So yeah, so I was talking about these two approaches of how you can solve the problem or try to find solutions for a quantum control problem. Yes. Okay. So now we're diving into the game a little bit. This is one example of a problem that we looked into. This is, you have a crystal structure here, which is, let's maybe show this. Yes. Okay. And on each side, there is an atom trapped, an atom that is placed here. And on top of that, we superimpose of what we call an optical tweezer. So optical tweezer is this really powerful laser that will make a trap like this and will keep the atom here. And this trap it's really, really small, 1 micrometer. Okay, so you have the atom that's trapped here, and now this trap can be moved around different places. So you take the whole laser, so you take the whole optical tweezer and you can move it in different places. So this is one problem we looked into, where there's an atom in neighboring sites, each of these green dots, and an optical tweezer is superimposed on top of that so that it creates a trap, and then we move this whole atom inside that trap, okay? So this is what we simulated in the game. So this is the orange tiny circle that you see here, or ball, is basically simulated here. And in the game, we decided to show it as a wave function. That's also because when you have these atoms trapped, you have the atom in the ground state. When it's moving, then it becomes excited, it goes into superposition state. So we decided it was best to show it as a wave function. And also for players to give this new understanding of, because an atom has always been described as this round ball. We also wanted to give a new visualization to teach them, because that's actually the reality where we describe atoms and electrons with wave functions. Okay, so this is what the game looks like. I'll also do a screen. I'll share my screen. I'll play the game also now in front of you, so that you just have a feel of how the game fields. Okay, so the challenge here is there is an atom here with this red outline. One has to go from here, pick up this atom and come back. So the goal is to overlap the red and the yellow outline. So this is the initial state and this is the target state. So one has to go pick up this atom and come back. Okay.
Shaeema, if I can interrupt because there is a question from Auntie on chat.
Yeah, sure.
Auntie, maybe you can unmute yourself and ask your questions, and maybe it will be even easier, because I believe that it was related to one of the previous slides, probably.
Okay. Yeah, I think should I answer the first one and from Auntie, right? Yes, that was move from trap to trap or within a single trap. Move from trap to trap.
Oh, okay, thank you. So let's go on.
Yeah, and the next one is from Abdullah, I think. Oh, okay, no, that's a direct question to me. But okay, I can see it, Abdullah. You have a question on the game development. I'll come to that part. So maybe just wait for a little while, and I'll address that question. Okay, so yes, so here the atom is trapped. So I'm just repeating again. This circle is sort of the controller. I have to gradually move it, pick it up, and come back. And this has to be done within a time limit where one can see it here. And how best it overlaps, because we have to overlap the red and the yellow outline, and you have to keep the atom in almost the same state like it's here. So here it's in the ground state, but when you move it, it gets some energy, so it will get excited. So, but we want it to be still in the ground state when it comes back here. And that's where the hardest part comes. How do you move this atom? So then this is given by a measure of fidelity. And then there is also a way to, if you have something that's good, you can try that solution and then press optimize. And then the same solution becomes better. Okay. So I think now maybe it would be best to actually show you the game. And you also feel free to try the game yourself. I'll post the link here. Let me actually maybe stop share now, because then that'll be easy. And okay, chapter everyone. Yeah. Here I'm sending you the link of the game. So you can also try it out. And I'm also going to just try it out now and show it to you. Okay, so it's a browser-based game. Earlier, it was only a computer game that could be downloaded, and we couldn't have it on mobile because the game was really heavy. It needed the math library to get the real-time calculations. Okay, so let's try to go for bring home water. This is the game. So I'm going to go pick this up, and my time is running out, but as I want to go pick it up, and then I can see that the atom is now all over. So I don't really have a good score, good fidelity. It's 0. So let's try again. So replay. Then I can pick it up. So now I think this is at least better than the last time, but maybe not. But I can use this optimizer. Oh, I think this optimizer is not working anymore on the. So this was when I made it. It was 2 years now. Okay, it must be 4 years ago now. Like if I count back from today. So now this game is on the website of the research group that I worked on. I worked with. Yeah. So basically, this is to give an idea of the game. This is the control problem. One has to go pick it up and bring it back. And you can see that every time you move the atom sort of sloshes like a liquid and tries to go outside the trap. And this is what actually also happens experimentally. If you are moving an atom from a trap to a different trap, you will find that the atom gets excited. And this changing of the wave function is basically the atom going into a different superposition of different energy states. And that's why you have the wave function that's not in the ground state anymore. So this is what we made players play. Maybe I'll just go back to my presentation, but I have to switch. Let's do this. Yeah. Yeah, so what I just showed you was this game, was this level. We had different levels, and this is the bring home water, one of the scientific levels. We had to move the atom. And now what we call is you're moving a single atom. You're moving, this is the initial state, target state. This is a potential function that is dynamic. Like when I showed it to you, I could move this potential. I could move this potential from here to pick this atom and come back. Okay. So, and this potential function is a Gaussian tweezer potential, which is used experimentally. And this is what we tried to model in the game. Model this experimentally. It's been done in University of Vienna, where we sort of took inspiration from this experiment. We didn't exactly simulate what the experiment did, but theoretically, or sort of the basic framework, what could fit into what could be, how do I say? We didn't, okay, maybe I should say it this way. We didn't really put the experimental constraints really in the game. It was more, we simulated it, but we had it more free flowing without too many constraints. The only constraint we had was this, that your control had to be within this box. So you couldn't move the atom everywhere around, but it had to be inside this dotted box. Okay, so these are some mathematical functions. Just to give you a feel of what went behind the game. So we had to mathematically figure out how would controlling the atom be. This is the control function. So now this potential function could be controlled both ways, along the x-axis, like here, and along the y-axis, which was sort of mentioned in the game with the green and red arrows. So u to the power 0, which is basically, we're naming the different controls here. So these would basically feed into these equations, and then this potential function would change. So again, it's okay not to sort of dive in and understand each equation here. It's just to give you a feel of what went behind. And then when we move this potential, or we move this trap, the atom evolves in time, and this evolution was given by the time-dependent Schrodinger equation. So all of this was running in the background when players would play the game. Yes, this is the link. I think I already shared it. So, okay, so now this game took 2 years, and we went from different schools. We mostly went to schools because that was the way we could collect data. And for schools, it was also nice that they got an introduction to quantum physics, and they also could play games. And for us, we got students to play the game and collect the data, because then we wanted to analyze data and see how did the solutions from the players, how were they as compared to a purely computational algorithm. And we could find that the player contribution was comparable. And that's where we actually saw some very interesting things about a computer would likes to be really precise, right? Like if you give it will try to find something really precise. But if it's really in a bad solution landscape, it will get stuck there. But human beings or players we saw could adapt very quickly. If some way of playing was not working, they switched to a different way of finding a solution. And that adaptation from one side to the other way of playing gave us a variety of solutions, which a computation algorithm couldn't give us. Like I mentioned, players could also optimize their solutions, but we actually saw players did not use that so much. That's something scientific, as researchers, we do it. Now we provide initial solutions and then we optimize it, but we also thought, what if players also optimize the solution? And this, we wanted to give a feel of maybe players can select which solutions they want to optimize. They did optimize, but they would end the optimization very early. We just think it was very boring for the player to see something that was being optimized, because they wanted to find out more new solutions. Because later we also spoke to some of the players and did some interviews with them. And this is when they said that the optimization feature was quite boring for them. And that's why they didn't want to use it. But it was good learning for us, because then we thought, okay, we want to give players all the tools, but it also gave us feedback of maybe the players don't want to use the tools, because it also has to make sense for them. It has to give them real-time feedback very quickly. It has to be interesting for them. Yes. So since players did not optimize too much, what we did, we took the players' initial solutions and then we optimized it using a computer cluster and doing the algorithms. So here we have a human and computer collaboration happening. We took the solutions from the players and still worked on it using the algorithms to optimize. And this was the most promising way of actually finding the good solutions. But it's still open to discussion because we still need more data to confirm this. Yeah, but this is sort of more a case study of what, yeah. The other direction, my research group, at least now they're taking it, is that whatever solutions were generated from the game, if they could extract some heuristics or a particular kind of pattern of how players played the game, and these patterns would maybe feed into the algorithm. So the algorithm would be designed based on the human input. So these are some open questions and areas that have been left open for people to experiment. And my research group is currently experimenting, but ever since after my PhD, I haven't worked on the game as of now. So yeah, so that was the part of the game. And I think here also I'm going to stop and maybe ask if there are any questions.
All right, thank you. Thanks, Shaeema. Thanks very much. There is a question from Antonio. Do you think that game interface design could affect player-generated solutions? Or maybe playing controls could affect these solutions also?
Yeah, it's both. The game interface actually has a huge role in how we get on the quality of the solutions we get. Because if they don't know the background of the problem and they don't know quantum physics, then all they have is that interface. And so giving them that interface is very powerful to get solutions. And I think I will show a few things after this slide on the second part where I'm going to talk about how the game was built, like showing you some old versions and then the latest version. Yeah. So, and what was the second part of the question? I think there were two parts, right? Or maybe playing controls could affect these solutions or these solutions also. Yes. So use how players use the controls also affected the solutions. There were some players we found both from the data and from the interview. Some players did not have the patience to move the atom very slowly. So they would want to move it really quickly. And that's when you're doing the control so quickly. But then the atom gets very excited and then you don't get the target state you want. So it had a reflection of some players' personalities as well. Of some wanted to generate many solutions, but didn't think about if the controls were good. But they thought, let me generate so many that out of the so many, some will be really good control solutions. And some were very patient and said, okay, no, I want to take this control. This is giving me something good. Let me make this better and better. So we did find two groups of players. Yeah. Great. And is there any other question? Thank you, Antonio.
I don't see any more questions on our chat. Maybe someone would like to unmute himself.
Okay. So great. Then I'll just move on now to the second part. So now I told you about the problem, the mathematical framework, and the game, but actually there's a lot that happened behind the scenes. It took 2 years, and that's where I want to show you of how this game progressed. I didn't have any background in game development, so I collaborated with a team. So the research group already had this team. So that way I was really lucky to come into a team where there were game developers already. Yes. So let me start. So now you saw the version of the game that's online, but this is the version that was one of the first versions, and it looked like this. So instead of, so you can see how much it's changed from what we started with. And this is the first interface actually that went out to schools. And that question that was related to, I think Antonio asked about the interface exactly. This was the This was the interface. We got very different results when it was an interface like this, and we got very different results when we had the new interface. And that's what showed, and it could be very small things like having a slider. Here, the interface, all the interactive elements were using a slider, and this slider. But what happened was having a slider made it difficult for them to have something to control it properly. So in the later version, we had more like a switch you could optimize. So it was just on off and they could see the number. So these small things made some difference. We also, the first version, if you can see, it had norm T, fidelity, O step, like the terminology that was used was just so far away from what players would be able to understand. So this norm T was basically language for us, which was normalized time. So we called it norm T. But this was the first interface that was ready to do a test with some of the players, which gave us a lot of feedback. Simple things like, should you have sliders or should you have something which is more button? There was this cat. The cat was supposed to be the cat gets longer if you have a good solution, and the cat becomes shorter when it's not a good solution. So there were these other fun elements as well. And later we had to remove some of the fun elements and make it very true to the science. So all those are very difficult discussions we had, and also we had arguments because someone wanted to keep some feature and someone didn't want to. So as you can see, this is what we had started with, and then this is what we ended up with. Yeah. So earlier the time and fidelity would show here, and then later it became a time box and a fidelity box here. Optimize was a slider, and optimize became like a button. And this is the very initial. I think it all started with sketching on paper. When we looked at the problems, and these sketches had to be done when we were talking to the game developers. And I think we had sketches for every level, and this is just one level. And we have 3 scientific levels with some tutorial levels. So in total, there were about 20 to 50 sketches and we had this room full of all these sketches and everything. And till today, if I still want to make a new game, I still start out with paper, drawing out some stuff. And I think it's also maybe could be true for most of you when you're doing the hackathon here, when you brainstorm and have something. Yeah. But I guess you're also remote, right? Yeah. But you probably use some online tools to sketch out things. So just is to show you like how the thing evolved from an interface that was like this to something like this. And this was the very basic stage where it just had sketches. And now I want to dive into the team, how many people were involved. We were 2 physicists, me, and there was another PhD student. So we were 2 PhD students. And our main role was, what problems should we show in the game? So what problem formulation? So we read research papers and we said, these problems are relevant today for quantum control. And because these quantum control problems are connected to how you can build quantum computing architecture or quantum sensing and so on, because the problems also have to be relevant of what we want to formulate. We also looked at the programming. Now, not me so much. I'm not very good in programming, but like I could still like do some certain tweaks to what we had written. But my colleague was more in that lead. So we sort of divided. I did problem formulation, so more looking at the research papers and selecting what problems we want to simulate. And my colleague, he was programming it in C++. We used this Q Engine software library, which was also designed in our research group by previous PhD students. So we used the software library from there. So once we had the basic problem formulation, we knew, okay, this is where we're going to write it and program it. We worked with 2 game developers, and this was a back and forth process. So the sketches I showed you, it started off with that, saying that, okay, we want to simulate these problems. This is what it looks like on a sketch. So then after they received the code from us in C++, they did the sort of game engine part. So the whole game was on Unity. So there had to be this whole binding between C++ because they were writing everything in C#. So there was this also binding between what we had written as physicists and what the game developers were writing. So that was also a lot of back and forth to make sure what we wanted was not getting lost in the game after they had put it in the game engine. Then the game also has to look nice, right? I mean, if we just had a bunch of only physicists doing the game, we would maybe have not paid attention to how the game would look and how the visual elements should be, what colors should be, theme. So we also had a game designer on board. This was at the very last stage. We first made the very basic prototype and said, okay, we had the problem simulated correctly. We had it running on the game engine properly, and then later we started making these tweaks on game design. But it's a really back and forth process. I think before the final version came out, we had at least 4 versions. We had one version, we tested it out. Then we had the second version, tested it out, because we also had to check if the game was working smoothly without bugs and so on. Then there's another huge part we had was completely at the back end was collecting all the data, because whenever players would play it, this data is getting collected in a database. So we had one person who was just in charge of this data collection aspect, because the data had to be collected first anonymously because of GDPR rules. So every player was just like a number. And then the data that was collected was when the control was moved, the position of the mouse pointer with respect to time. So at every instant of time, where was the mouse pointer? And these mouse pointer coordinates were constructed to form the control, which we analyzed. So this was us, the entire team, putting into different aspects of our expertise into the game. And also, I would imagine also in the hackathon, this is something that all of you will come with different skills. And it's a huge asset, because it's okay to not know everything on your own, but you do give your expertise, someone else can fill in with theirs, and then you have something that's really beautiful and a game that could be fun. You're simulating something in the sort of true sense, right? Like you're keeping the science intact. And if you don't have any background in programming or quantum physics, but you are more into art and designing, your perspective is very valuable to make the game look nice and approachable. You don't want something that's not approachable, because then no one will play the game, right? So yeah. I think I'm actually at the end of the talk. This was all I wanted to say. Just give a brief introduction to the game, share my own experience. And right now, also in my company, we are hoping to build more games, but this is mostly for education, that we want to do it with schools. So maybe have a science kit where students can put some things together, program a little bit, and then they have a game ready. So if you want to find out more about what's coming up in my company, you can, this QR code takes you to my website, and we're also on social media, so you can follow us.
Okay. Great, fantastic. Thank you, Shaeema. I can see that there are some questions on our chat from Abdullah. Mm-hmm. In fact, there are several questions, so maybe you can first read them. Maybe it will be easier.
Yes, I will start. For the development, the several. Okay. Just thinking. Here, game development takes lead over theoretical physics. So how important is game development here as compared to theoretical physics? Since many people are from theoretical background and they find it hard to develop game. Yes. And that was also, I recognize this question, because that was exactly when I came in to do my PhD, and my supervisor said, okay, we have to create this game. This is the research question we want to address, if a game can generate solutions to quantum. And then I was also thinking, how do I do this? I have never made a game. But I think in this case, if you have to collaborate, and collaboration is the key. And also with collaborating, it also gives you many new perspectives of how you thought of the problem, and someone who doesn't know the problem, the questions they ask you will help you even refine what kind of game you want to make. So it will be hard if you don't have your own for example, for me, I didn't know how to develop a game. And I think collaboration for me was the key. So what's important is to have come with a mindset that this is a collaborative project that we're going to do. So you will do your part and I will do my part. And that we divided our roles very clearly. And I think that's what helped. We said, okay, anything to do with the game development is yours, but anything to show the physics is my part. So I will only show the physics and give it to you in a particular format, where in our case was we gave them the code like in C++. Yeah. For the development part, what language and is the key as we use. So for as physicists, we did everything in C++ and we handed it over to the game developers. They use C# and they did some magic with C# and all of that we never got into. At the end, what we did was we like, okay, let's meet in 2 weeks and you show us what you have. That's what we did. We would have every Friday meetings to follow up what the status was on their end. So let's say if some of our code was something that they didn't understand, we had to send them new code and then they worked on it. So yeah, it was, we divided it like that, yeah. Then another one, we are working on a bigger project and need your views and suggestions on the topic after the hackathon. Yeah, of course, Abdullah, I'd be happy to help. However much I can, and I can, in case there are some questions I can't answer, I know some other people who also made games in my research group, so I can connect them to you who are already in the research group. So you can get more advice as well. Okay, for writing in those languages, one needs to be experienced in game development around 3 years or something, especially CE. Yeah, and here, I think I was lucky to come into a group where people already had this experience in game development. And I'm just trying to think from the hackathon point of view, if you think you don't have that necessary, it also depends on the ambition level of the game. For example, if we wanted this game to be out, go to school, so it had to be a really finished product. But sometimes you also make a game just as a passion project and that you want to put it on GitHub. So then there are different levels of ambition of that project. If you have a really big project and if you want the game to be like a blockbuster game, be it on App Store and spread it around, you need a full team. And but how a hackathon can help you is a hackathon sparks that gives it a head start to start something. So if you think you don't have full experience at this point, I think it's okay. You still have a minimum viable game that can be ready, which you can work on it later when you find other people with more experience, or maybe when you get more experienced as well. Yeah. Okay. And then there's a question also, but I think this is just directly to me, but I think I have observed that some of the games doesn't have quantum aspect to it. They're only made with JavaScript. Your views on this, since it's a quantum game. Did you mean observed some of the games? This is which games? Are the games on my research group's page, or which games did you mean? Abdullah, maybe if you want to.
Yes, Abdullah, maybe you can unmute yourself.
Yeah, hello. Yeah, is my voice audible?
Yes.
Yes.
So I'm talking about, I've just observed like a few games from the previous jams, like actually they were built using JavaScript, and I think some kind of web development languages like JavaScript or any other languages which is using the front-end development, web development. So the thing is, like, what I've observed is like they were missing the quantum essence and the quantum aspect of it. So I just need to have your opinion on this, like what is that, like we can make some games related to this or like that?
Yeah, I think games related to this where you have to also collect data. You can make some you can make games that have some more simpler simulations. If you don't have data collection, I would suggest to actually go with browser-based, where it could be JavaScript, or you can have using Python as well. I think you can create like a browser-based game. But if a game has data collection involved and where you also get feedback real time, I wouldn't suggest, I think, JavaScript. Yeah. Yeah. Was that?
Yeah, it was answered. So for
Okay.
I think I wanted to reach out for a different thing. Like it's not a quantum game, but we are researching on a different project. So we need your suggestions and feedback on this. So we are planning to reach out to you. So if you don't mind.
Yeah, of course. No problem. No problem. Reach out to me anytime.
Great, fantastic. Do we have any more questions? All right, I don't see more questions, so let me now stop recording.